I'm Dr. Sortomme, and I'm giving my presentation on integrating electric vehicles into the power system through VehicletoGrid. And if that doesn't make any sense to you now, that's okay, but hopefully it will by the time I'm done. Just a brief little outline, which also may not make an awful lot of sense at first. Introduction to electric vehicles, VehicletoGrid and energy markets, unidirectional VehicletoGrid or V2G on distribution systems, bidirectional VehicletoGrid problem, talk about some electric vehicle load modeling, some V2G with renewable energy and microgrids, and then conclusion. So first of all, electric vehicles. There's some lower end electric vehicles, Nissan Leaf, Mitsubishi Myvi, some really high end electric vehicles made by Tesla, fancy Roadster, Model S, $100,000 cars, $30,000 cars, if you can call that an economy car. So they look cool, some of them. Why do we care? Some people care about electric cars because of energy independence and energy security. The electric grid, almost all of the fuel used to create electricity is produced in North America. I'd like to say all in the US, but we import a lot of power from Canada. They've got a lot of hydro up there. It's also not dependent on a single fuel source. So if oil spikes, the price of coal isn't really going to spike, or the price of natural gas might not spike, or hydro or nuclear. There's also reduced environmental impacts of electric vehicles. There's higher energy efficiency to convert fossil fuels into electricity at large centralized plants and transmit it to the batteries than it is to try and burn petroleum in the engine. So you have higher efficiency there. It's also easier to control emissions at a few thousand large centralized power plants than it is at hundreds of millions of distributed little engines. And also, you can potentially run on clean renewable fuels such as nuclear, hydro, wind, and solar. And then probably the biggest one for me is, well, not for me, the improved driving experience. If you've never gotten behind the wheel of an electric car, they have instantaneous response to the pedal. They have 100% torque at 0 RPM, so you can get off the line like nothing else. There's also no engine noise or no engine vibration, so it's smooth, it's quiet, it's responsive. This is a premium sort of driving experience that a lot of people will pay a lot of money for top-end BMWs, Lexus type of car to drive really quiet, be sporty, and that just comes with any electric vehicle, not just the high-end. So those are the three main reasons. Let's talk about EV adoption in the US. A few years ago, they made some ambitious goals of putting 1 million plug-in cars on the road in this country by the year 2015. As of January, we're about at 72,000, falling short. However, the rate of adoption is increasing. And though we probably won't hit 1 million by 2015, there's a very good chance that we'll have several hundred thousands of them. And also, a lot of those will be clustered on the coastlines, so they'll make more of an impact because they're localized in a smaller area. Interesting thing to note, the majority of the cars so far sold have been plug-in hybrids, the Chevy Volt and the plug-in Prius, rather than the pure electrics. But we'll see how that turns out in the future. Either way, they all plug into the grid. So let's talk about some charging issues with the electric grid. Why do we care? Here's a picture of 4 Tesla Model S plugged in at superchargers. Each one of those is a 90 kilowatt charger. So that's 360,000 kilowatts being pulled. No, 360,000 watts. 360 kilowatt being pulled right there on the grid from just one location, and they'll be there for like 30 minutes, and they could go away, and then that load just drops. They'll come back, the load picks up. Kind of major on the electrical system. Problems with electric vehicle charging for the bulk power. We need more energy, first of all, so you've got to burn more fuel. If you are a hydro utility, like we have in the up in the Northwest where I'm from, that means you've got to spill more water over your dam or through your turbines, and you only have while it's clean and renewable, you only have so much water that flows down your river in a given year. So you can have supply shortages potentially. You're also going to have higher peak loads, and that means you'll have to have your least efficient power plants, your peaking units, often running for longer during the day, so it's worse efficiency. Those are also the biggest polluters. And you might not have enough capacity to meet this extra load, so you'll have to go build more power plants. So then there's the distribution system from where these guys are actually plugged in. Well, if you're just plugging in at your house, an electric car could potentially double the load in your house. So it's not insignificant, and the distribution system wasn't designed when they strung it out to handle that much load. So it's going to double your load. A lot of EVs may cluster, and the clustering is going to be much worse on the distribution system than the transmission system, because I go out and I buy a Tesla Model S and I think I'm really cool, and my neighbor's like, well, hey, I'm going to buy one too, and some other guy wants to look cool and trendy, another neighbor, and he'll go buy a Leaf because he doesn't have as much money as me. And you know, I bought the cheap Model S, the $50,000 one, but I wanted to look cool and pretend that it's the $100,000. You know, you get that sort of stuff. And so then they're all charging on the same distribution transformer, and then you have these localized overloads and voltage problems just because neighbors compete. You see it. So how do I intend to solve this problem? I want to do it through vehicle-to-grid, or V2G for short. And this would be the intelligent charge control of the cars. So when they're charging, they don't just plug in and charge. They plug in, and then you control how much they charge and when. And sometimes you can discharge from the battery, sometimes you don't. The V2G allows the electric cars to not just vary their charge rate, but to also provide valuable services to the grid and participate in energy markets through an entity called an aggregator. And the aggregator takes bids from lots of electric cars. It knows will get their location, get other details through the internet or potentially a wireless provider. Aggregator will then contract through the grid operator, through the energy markets, provide services, and control the car charging, get money. Some of the money goes back to you. And then you have a nice system where we've got the problems of electric cars being solved through controlling the charging so they don't cause higher peak loads. And you have an incentive for the customers to sign up to allow this charging. You have an incentive for somebody else to make sure to manage it. And everybody wins, especially the aggregator. So what sort of energy markets can these electric cars play in? Here's a daily load curve. It says megawatts over here. That the Mac decided to ruin all of my beautiful y-axis graphs for some reason. It didn't like it. So here's a daily load curve for the Bonneville Power Administration. The first market would be the energy market, which would be economic dispatch, where the generators will schedule one-hour blocks of energy that they will run at a certain level for an hour, and then the next dispatch period you'll have another mix of generators, but they'll run at a flat spot throughout the hour to try and meet that load. Clearly that doesn't meet the load exactly, and in the power system you have to have a perfect generation load balance at all times or else it'll break. So you zoom in on that top part and you see you have this high frequency component, and that is met by generators that every 4 to 10 seconds respond to the fluctuations, and they call it regulation. There's regulation up, which means increased generation, regulation down to decrease generation. And then there's the gradual increase of load as well that's taken care of through balancing markets. So you have this regulation that's market that does that. And then, as you see there, where suddenly a chunk of the generation was lost, you have emergency reserves that will have to come on where other generators will turn up to meet that loss of load. So that's the responsive reserve market. So electric cars can participate in these markets without discharging their battery in what I like to call unidirectional vehicle-to-grid. It involves the electric cars setting an average charge rate called a preferred operating point, and then they can increase and decrease their charging to participate in these markets. They perform regulation up by decreasing, because increasing generation is analogous to decreasing your load. They can also perform regulation down by increasing their load. And there you have, by adjusting your charge rate, you can now participate in these markets. And you don't discharge your battery into the grid, and that makes a lot of people happier, because if you own an electric car, you don't want the utility to come and steal your charge and leave you stranded. If you're a utility, you don't want to have to worry about all the interconnection issues with wherever this person plugs in. So now we have an entity called an aggregator, and he's going to contract lots of electric cars and sell it into these markets so he can make money. So if he can make money scheduling these cars, he wants to make the most money because he wants to have a good business. So he's going to optimally schedule. He's going to look at his own profits. And so this aggregator that we looked at, this imaginary aggregator, says he will take a percentage of the money he can make on the market for himself, and then he'll give the rest of it to the customers, and that's sort of their incentive. Let me play with your battery. I'll pass along, you'll get a benefit. Then he charges them a markup on the price of energy, because he has to take the energy and get it to them. That's what all distribution companies will do. And because he's passing on the real-time price of energy to the customer, his costs for this scheduling, at least, are constant. There's other costs that the aggregator may have, but as far as in the context of the scheduling, they're constant costs. The aggregator here can sell regulation down, regulation up, and the responsive reserves. His constraints will be the charger limits. You plug in your car. This charger there can only handle maybe 6 kilowatts. Your internal car charger, however, may only be able to handle 3 kilowatts if you've got a Nissan Leaf. So whichever is the smaller of those is your maximum charge rate. And you have your battery capacity limit. You may not be able to charge your battery to 100%. If you have a Tesla, they usually set that at about around 90% to keep it so the battery life is extended. If you keep your battery at 100% charge, it wears out faster. Then your availability. If you're driving your car, the aggregator can't sell the ability to increase or decrease charging because you're gone. And you can leave whenever you want, so he has to take that into account, because he better not schedule. You don't want to sign up for this service if he says, no, you can't leave for another hour because I just sold your stuff on the market. If you've got a car and you want to go, you're going. And then, of course, the ancillary services constraints. The aggregator can't sell negative values of the different capacities, because that doesn't make an awful lot of sense. So that leads us to what I like to call the optimal combined bidding formulation, or the OPTCOM formulation, where it maximizes aggregator profits, where your variables are your preferred operating point, your ability to increase your charging for regulation down, decrease your charging for regulation up, and decrease your charging for responsive reserves. And I apologize that the Mac didn't like the Microsoft equation editor and kind of skewed some of those numbers. This, of course, is subject to your battery capacity limits. You can't overcharge your battery. And this looks at how much you expect based on your schedule to charge into the battery plus your initial state. This one looks at the same thing minus any scheduled trips that you're going to take, so subtracting the energy off. And then this one handles the fact that since these are expected values and the dispatch may be higher than that, the closest scheduling period will always be able to meet 100% dispatch, just in case for some reason it's called on, you don't get in trouble with the grid operator and you can't make it. You're also subject to your charger limits, where you can't discharge and you can't charge more than your maximum. Your EV availabilities. This is a binary variable that's 0 if your car is driving, which drives this to 0, which means everything else becomes 0 and your car isn't participating, or 1 if you are there, which means the aggregator can do something with your car at that particular time. And finally, the ancillary services constraints, which says, yeah, you can't sell negative values because that doesn't make any sense, and you can't say you can reduce more than you are currently charging at, because then you'd be negative, which also we say you can't do. And the beauty of this is it's a linear program, which means we can solve it. We can guarantee optimality. We can actually solve it pretty quickly and efficiently. Some support equations to this formulation is your income from your aggregator, the price of your regulation up times the summation of all of the cars' capacity, regulation down times the capacity, responsive reserves times the capacity, EV percentage, which is how much you know that some cars are going to leave before the hour is over. So what percentage of them do you think are going to be there at the end of the hour or during the hour? That's how much you plan on for that hour's worth of income, plus your markup on the price of energy against how much energy you expect to sell. You find the expected value of the vehicle-to-grid services dispatch based on historical values, the probability. Look at the distribution to say, if I sell regulation down, if I sell a megawatt of that, how much of that megawatt hour do I expect to actually be dispatched? You do that for each service. Your unexpected departure compensation. So if a car leaves, every other car needs to slightly increase their dispatch to make up for that loss. And so here's how much each car needs to under schedules to make sure they have the ability to over dispatch. And then finally, here's how much energy you expect to gain in a given hour, which is your capacity of your increase times the expected value of that, plus your POP, plus your expected values of the capacities to decrease. So what happens if we had an aggregator that were actually doing that? We'll look at a case study and say if we had an aggregator in Houston, Texas. Look at a simulation of back in the summer of 2010. If from July to November, November 30th, there was an aggregator that was doing this. And if, say, he gave 80% of the money he made on the market to the customers and kept 20% for himself, and then charged the customers a mere 1 cent per kilowatt hour over the spot market price he was paying, what would it look like? Of course, scheduling 24 hours a day, looking in the ERCOT market in the Houston zone, because he's in Houston, Texas. We had a hypothetical fleet of 10,000 different electric cars. There have been 3,000 Nissan Leafs sold. It was just cars that were on the market at the time. So what if we had a good mix of different cars? How would it look like? We're going to examine one day in that to see how the optimization works, first of all. So this is August 2nd, 2010. You have the 3 different services. You can see at different points of the day, different services are the more valuable service to be selling at that time. And also the price ranges somewhere from $30 a megawatt down to $3 a megawatt. The optimization sells the regulation down when the regulation down is at sort of a local maximum right there. During the really high peak prices up here, it sells lots of regulation up. And then sort of there's a interesting hodgepodge of what it sells here, and that's because this is also the time when the cars are leaving work and coming back home, and so you have limited availability after 4 o'clock. And so you sell what you can. Your responsive reserves don't really get sold much until the very end of the day, because those are almost never dispatched, and so that charges your car. The sooner you charge your car, the sooner you can't sell money on the market, so you don't want to do that to the very end. So the optimum behavior is what you would expect given the conditions of everything. The total study results show that with 10,000 cars, your aggregator in this 5-month period could make nearly $200,000, provide an average of 12 megawatts of hourly regulation capacity. Customers will end up with their payments only paying less than 2.5 cents a kilowatt hour for electricity, which I don't know how many of you pay your own utility bills, but that's pretty cheap. My parents still pay cheaper, but they live in a hydro place. So you see that the vehicle-to-grid can provide significant regulation and reserve capacities and can generate some valuable revenue for your aggregator and for the customers. However, We didn't consider the distribution system, which is where I said most of the problems would come on. However, these can be included through feeder-specific load constraints. This feeder-specific load constraint would keep the maximum electric vehicle load on the feeder below a certain level, and I'd call that the opt-feeder scheduling algorithm, because it makes sure that what you're doing doesn't harm the distribution system. Feeder load constraint looks like this, where you have the maximum of your base feeder load plus all of the electric vehicles on that feeder and their potential to increase, and make sure that stays below the maximum that it used to be, because if not, you can have bad things happen on your distribution system where you blow stuff up, and nobody wants to blow up their stuff. So looking at the same group of electric cars on ERCOT, you have distributed amongst 50 different feeders of 3 different types. We looked at feeder voltages, losses, and line overloads to see how the 2 algorithms compared. We had one feeder type that looked like this, another feeder type that looked like that. EV loads are distributed at all the little EV electric vehicle points. And our final feeder was much bigger, looking like that. The results showed that, of course, the losses increase when you add these electric cars. When you do the feeder-specific constraint, you can reduce your losses by over 3%, which is good. The maximum line currents decrease, and you see the overloads that if you don't look at the feeder constraint, you have 35 instances over that 5 months where you overloaded your feeder, and that could have potentially blown something up, and then everyone would have lost power. However, by putting on the feeder constraint, you can avoid that. Looking at voltages, the ANSI standard says your voltage must be at 0.95 at 95% or higher. And if you go lower than that, you're in trouble. The base case was above it. The opt-feeder algorithm also stayed above it, though barely. But the unconstrained optimization went below it nearly 3,000 times over the 5-month period. So we can see that the system impacts. Looking at the economics and the larger system, this is the peak load that would be added by the electric cars on the bulk power grid. Unconstrained could be up to 45 megawatts, whereas average is about 2 megawatts. Whereas the opt feeder, the maximum is never above 5, and the average is less than 1. So from the bulk system perspective, this chart, having this constrained optimization is much better for them too. But it cuts down the aggregator profits. Also cuts down on the price of energy that the people have to pay, because it shifts more of the charging at night when it's not as expensive. So, if the aggregator is a third party, you'd say, who cares? Our feeder load constraint can eliminate the overloads, the voltage sags, reduce the losses. And who cares about the aggregator profits? But if the utility is the one that's doing this aggregation, they can look at that and say, well, is that the most cost-efficient way to stop the lines from getting overloaded? Or maybe with this much money times 10 years, we'd be better to invest in some fixed capacitor banks or some other bigger transformers. And so the economic comparison can be made. So what if you want to discharge your battery? What if you want to have your own little backup power grid, or you want to sell on the energy market as well? It works very similar to the unidirectional, except now we can set our preferred operating point at 0 or anywhere in between there, and we can go negative. Allows you to participate in energy markets, but you have to account for battery degradation and people's minimum customer driving needs, because if you're commuting to work, you better have enough to get home. There's 2 big complications of trying to formulate an optimal scheduling this way, and that's round-trip efficiency abuse on the part of the aggregator, and then formulating this as a convex optimization problem due to the nature of battery degradation and constraining the battery SOC. What is round-trip efficiency abuse? I'm an aggregator. I make lots of money selling energy to the car. I make money in the market, but I also make money selling energy to you. I know that your battery is not 100% efficient. So I can discharge your battery to 0 without paying you anything, and then charge you to fill it back up, and then discharge it again. So if here's the electric meter, which is where you pay for all the power that comes in here, here's your car battery. You buy 4 kilowatt hours from me. Your battery's 90% efficient. You get 3.6 kilowatt hours in your battery. Energy price doesn't change. I discharge your battery. I want 4 kilowatt hours. So you just take 4.4 kilowatt hours out of your battery, 90% efficiency. I pay you for 4 kilowatt hours. You just lost 0.8 kilowatt hours of energy out of your battery, and I didn't have to pay you anything for it. So clearly you need to have a way to stop the aggregators from pulling these shenanigans like this. And you can do that through a discharge compensation term. That is 1 minus the efficiency squared over the efficiency times however much the aggregator makes for selling you energy. And that will mean if he discharges anything from your battery, he's essentially paying you for that 0.8 kilowatt hours that you've lost, or however much that you lose. And so he'll only discharge your battery if it actually makes economic sense for both you and him, instead of just running your battery down. Though still, the aggregator can't solve this problem because it can be tricky, because your battery discharge cost he has to pay whenever your power draw is negative, but not if it's positive. Traditionally in the literature, people would give an if statement for this. Well, your degradation cost is 0 if you're positive. It's some value when you're negative, depending on the car and the type and how you're monitoring. And we'll have a nice if statement, and we'll use a dynamic programming, and we'll solve it, but that takes too long. So you can actually take a piecewise linear epigraph of this and say if you take negative deg, add to your objective function and put these two constraints, then you say your battery degradation is essentially this. So whenever your power draw is negative, the aggregator is paying a degradation cost. When your power draw is positive, you pay 0. And so that way you've solved what was once thought a nonlinear problem. You've accurately modeled it linearly. The other problem is battery state of charge. Your capacity to charge or discharge in the next hour depends on what it is in this hour. So you've got one state, your future states depend on it. Normally you would solve such state problems with a dynamic programming as well. But you can linearize it by constraining the cumulative sum of the expected power draw of the electric car over each time period. So for every time period, you can constrain the max, how much you think is going to come in the battery, to be less than your max, greater than your min. And so you sum for the first time period and make sure it's within those constraints. And the next scheduling period is within the constraints, the third, fourth, fifth, and so on. And that way, instead of having a dynamic programming with multiple states, you have however many scheduling period constraints, and you can solve that. So now that we can solve the problem, let's compare it to our unidirectional. First of all, we see that whereas unidirectional made 190,000, this is making millions. If you look at different battery replacement costs, because that's your biggest issue now, how much do you have to pay the customer to replace the battery? Is the battery really expensive, $800 per kilowatt hour of capacity to install, or is it really cheap, $200? Right now we're sitting somewhere around $400, give or take, depending on the car you buy. The total net revenue that you make is about the same, with a little less as it gets more expensive. Though from the aggregator's perspective, the cost of the battery determines how much you're having to give to the customer to offset the costs. From the system point of view, the system likes it because on average you're discharging, so instead of being a burden, you've now become an asset. And when compared to the unidirectional vehicle-to-grid, the profits are nearly 10 times higher. So if you want to make money on 10,000 cars, see if you can discharge them, and you can be a millionaire. Unfortunately, all of these models didn't look at how the EV itself will behave when the system changes. When you change the power flow, it will change the voltage. And so we need to research how EV loads change with respect to system voltage. So we took 4 different cars, a Nissan Leaf, Tesla Roadster, Model S, and a Chevy Volt. We plugged them into a nice Variac variable power source and monitored with high precision the voltage and the current going into these cars so we could find out how much power. Plotting the power draw against voltage sweeping from 100 to 130 volts shows that each of them behave remarkably different, especially the Nissan Leaf that really wants to not vary at all, but it can't after a certain point, and so it has 3 different levels. The Chevy Volt clips it when it gets to the top. The Model S and the Tesla Roadster are linear, but not at the same level linear. So each EV so far measured behaves differently as far as the voltage response. So using a single generic model in your studies may give inaccurate results. How does this all tie into renewable energy? Wind and solar, 2 of the most popular renewables, have completely variable outputs that are uncontrollable. Here's one day of solar in Duke Energy. There's some nice, the clouds came in the afternoon, and there's your output. Here's a day of wind for Bonneville Power Administration, where it just does what it wants. However, if you have vehicle-to-grid, you can smooth those out to make them nice. So you can do renewable energy firming. You can also store excess energy, maybe from this peak, and sell, and then discharge it back there through the electric car. So you can use this to integrate renewable energy systems. You can also use vehicle-to-grid with microgrids. A microgrid is a small collection of loads and generation on the power distribution system. You can see here, it can actually disconnect from the main power grid and uses its generation and its battery storage and maybe other fuel and responsive loads to keep operating autonomously in the event of a grid disturbance. V2G can provide the battery energy storage if you're doing bidirectional, and also help maintain the grid frequency of your microgrid when you're island. So it's very valuable for small power system stability and control. Conclusions of this is that electric vehicles can, in fact, be safely integrated into the power system with intelligent charge control through vehicle-to-grid. The V2G provides significant benefits to all stakeholders, and so there's a very good reason to be pursuing it. It also has many additional applications in smart grid, such as renewable energy integration and microgrids. And there's still lots of research to do, and we're just getting started. So thank you. Any questions?
All right. Questions from the audience?
Yes.
The particular charging stations, I would imagine there has to be certain hardware built into those and algorithms that allow them to use.
There can be, especially if you're doing bidirectional. You can also do it. You can dispatch directly to the car without having to do anything to the charging station. The latest I discovered recently from talking with the people at Tesla that the Tesla Model S will actually, you could write an app that will vary its charge rate remotely from a smartphone. So another app from that would make it go to some central control center, and it can already set up so that it will, it can tweet its battery status, if it's driving, how fast it's driving, how far, how much energy it's using currently. It can tweet also its position, so you can know if it's charging remotely. The car does that by itself, and then you can write a program that will say, okay, increase your charge rate, decrease your charge rate, or just simply turn off or turn back on. So in that case, you really don't need any other hardware. You just need to write an app, and there you go. And I swear Tesla was daring someone like me to try and do it, because they set it up that way but don't seem to care that if you do it or not. They're not pursuing it in any way. So, yeah. Yes?
I have a question. Could you please go back to the slide where you tested all this, the charging profile
Yes.
of different vehicles?
Ding. Yes. Mm-hmm.
And for this, we do not see that much of variation actually. even the voltage variation is 100 to 125,
Right.
but the variation probably in the range of 15, 20%,
Yeah.
right?
Right. 15, 20%.
The question is, as far as I know, most of these batteries, the charger is a nonlinear load, it's a power electronics load.
Right.
And do you have an explanation why the charging profile, the power is changing? Because for a nonlinear load, its output shouldn't be affected by the input voltage.
That I do not know. I honestly believe with the volt, because as soon as it hit 120 volts, it clipped and wouldn't go any higher. I think that there's probably some in the battery management system, they say, here's the maximum power we want to come into the car and we don't want any more, and so they artificially clipped it. With the Teslas, I think that they're just trying to maintain, because you set the charge current of the car, so they're trying to maintain a constant current, so as the voltage goes down, the power will go down as well. I have no idea what the Nissan Leaf is trying to do. But you know, what it's not shown is then we got more Nissan Leafs and we went to different locations and we tried it and it all just matched up the same thing. So for some reason Nissan thought that would be a really cool way to have their power electronics behave, but no idea why.
What was the duration of this charging profile?
So yeah, these were charged over the periods of hours. It would set at each point for at least 5 minutes until it stabilized. With the initial testing, just to make sure, we would let it set at we would record the voltage and the power draw for an entire hour to see if there was any variation. And it would settle out after about a minute after we adjusted it. And so it would maintain a nearly constant at that given level for an hour, 2 hours at a time before we changed it. So we found through extensive testing that, you know, after about a minute, you know what it's going to be, and it will sit at that rate for the entire time. We emptied the Leaf. This is actually work that I've done at my job that I've been doing at Alstom Grid, where we messed with this stuff, where the company has a Leaf, and so we did extensive testing, and you know, we dropped it down to 115 volts and then just charged it the entire time, and from 0 to full at different times, and it holds pretty steady. There's a slightest gradual decrease with state of charge, but it's like 1% or less. Whereas you can tell it goes from 1400 down to 1150, so 20% drop within the voltage range.
That's probably for 100% adoption or 100%, like in order to use them as a dispatchable energy, you need a wider variation so that these chargers would have some features so that they are not designed to
Right.
live with the voltage.
Right. Well, no. This wasn't so we could vary the power with respect to the voltage. This was, we expect their nominal value, but because the distribution system voltage, or maybe the utility that's doing it, is doing some sort of voltage control, what are we actually going to get out? So if we're getting 20% less power from the car than we told the market we're getting, then we're penalized, because you do that across 10,000 cars and suddenly we ran up, you know, they said we need 2 megawatts and we're only giving them 1.8, then they're mad at us and we get penalized. So it's, when we're scheduling how much, we need to take into account the fact that what's the distribution system voltage going to be at the point of dispatch, and then how is that going to play with how much power we really think we have available.
I think my question was, they are not still ready to do the unidirectional V2G.
Well, the chargers say some of I think Eaton makes some smart chargers that can do the unidirectional V2G.
But not these vehicles.
Well, as I said, you know, the Tesla can, if you make some software. The hardware can't. This wasn't looking at the hardware to dispatch. This was just looking at the hardware for response. If we say charge at this level and the voltage is lower than what we expected, do we get it out? Well, with the Leaf is actually the most well-behaved with it until you get to about 117 volts, at which point it drops down discontinuously, which is really odd, because we tried to measure at 115 volts, and we tried really hard, and we could never get it to really settle because it was trying to put it in between the two levels that it wanted to operate, and it didn't like it very much. It would be very interesting to see from a power electronics angle what the heck is going on in there, but not my area of expertise. Yes?
So on this aggregator issue, where do you see would be the highest economic benefit? Because on the spot market, when the load is highest around like 5 o'clock,
Right.
5:30, on the spot market, it's the highest, the cost is highest at that point.
Right.
But it's the same time when all the people would return home and plug their EVs to charge their vehicles,
Right.
not dispatchers.
Right.
So how do you think the aggregators would find economic benefit at the highest point where the spot market is really volatile?
Right, and so that, now I gotta go all the way back to my, so if the aggregator just passes the cost directly to the customer, then you'll see here about 4 o'clock, right before everyone goes home, aggregator's like, yeah, you know, the reason the price is so high is because the load is high and there's lots of other things happening. Aggregator saying, yeah, let's sell that, or, you know, let's schedule the cars to charge a whole bunch, which isn't actually the best thing to do for the system, but that's where he makes the most money. However, if this is a bidirectional case, instead, that's when the aggregator's discharging the battery really high because he can make a whole bunch of money.
Well, but then at that point, at 5 o'clock, the EVs are going to act as a load and not as a generator.
You're right, and most of these times the EVs are going to act as a load. But even if, right, and so you get into the problem where if the EVs are acting by a load, you can make money by turning them down, but the system still doesn't want them on there, which is why when the feeder constraint occurred, you saw the big, or it doesn't have that, but when the feeder, because the feeder peak load would sync up pretty well with the system peak load. So you put a constraint and it stops them from being much of a load source at that peak power time because it's not good for the system. So what the aggregator will do is it'll set the car charging at 0, but then sell the ability to increase if for some reason the system needs more load, because for some reason if they're generating too much power, they either need to reduce the generation or increase the load so that the aggregator can still sell capacity during that time. It's sort of a, you know, you set the constraints on the system. If the system says, I don't want you charging then the aggregator just says, well, what else can I do to make money? If you can discharge, that's great. You sell your battery power. But if you can't discharge, then I don't know. So it's, yeah.
2 questions. One, with the power companies, when they are trying to switch between all of a sudden a spike in the load or a drop in the load, how much time do they have to be able to meet that demand without actually causing damage to the grid?
So like in the case of emergency reserves, a generator goes off or something?
Yeah.
Or just a big system event that occurs?
Yeah, suddenly everybody decides to turn on their AC unit at the same time.
Right. Which is interesting, you know, because they have that Earth hour where they're like, everyone, we're going to turn off our power at this time. I'm like, you know, that could actually be bad.
What's their response time to get the...
So regulation responds within 4 seconds. The emergency reserves is usually, they say you have to be online within a minute. So each market product, they have specific dispatch rules. So spinning reserve has to be able to come online to full within, I think, 30 seconds to a minute. And they have another set called non-spinning reserve that has 10 to 30 minutes to get up online.
Okay.
So stuff to start up. So they have the different markets. Regulation's the fastest, and there's spinning reserve. There's non-spinning reserve, which I didn't look at. There's other stuff. And so, you know, the system will say, here's your requirements. If you want to sell this sort of thing, you have to be able to meet it. And the system has to have certain amounts of these throughout the day. And they'll, you know, and so the market prices are affected by what resources are available to do this versus, you know, how much they say it costs. And for this study, I actually got all the bids for the ERCOT system. So we had the stack from the cheapest bids to the most expensive, and then you weigh your capacity. And the electric cars had a 0 bid, and so you would see how it would impact the market prices on there as they sort of played in that.
So then the second question is, if you're, say you have your vehicle plugged in and you are either, the aggregator is using you or not,
Right.
and then all of a sudden has to stop using you or has to start using you, and they keep oscillating between loading and unloading your vehicle.
Right.
How much damage is that going to cause the battery, or is the battery able to handle it? Or?
So for the unidirectional vehicle to grid, it doesn't matter. Battery issue, that doesn't cause. For discharging, it will cause damage to the battery, and that's why we had that degradation cost. And so it just depends on how much your battery costs to replace. So if your battery's cheap, it won't cause that much damage. If your battery's really expensive, you saw in the last term that the the bidirectional, stop. It wants to, okay, Mac won't let me go through it. The amount that you're paying to the customers for breaking their battery was more than twice as much money as you were actually being able to keep for yourself. So, 2/3 of your revenue were going just to compensate the people for trashing their batteries. So.
I guess better reframe the question, how much abuse can the battery take before you start seeing it? How tight of a time frame do they have between switching? Because obviously through normal use they will be loading the system and then discharging the system. So.
And that's a really good question, and different battery chemistries have different stuff where, some of them you can really high frequency changes, and because, you can punch the accelerator and then let off and have the regen take right on. And so essentially you're doing the same thing with this vehicle-to-grid charging, discharging. Usually what I found is that it wouldn't be switching from charging to discharging because you schedule the POP either deep within the discharging or high within the charging regime. And so you were taking advantage. So you're usually lots of charging with a little bit of discharge, but it depends on battery chemistries. And so modeling how that degradation takes into account is difficult. The value that I used was some researchers actually simulated what vehicle-to-grid dispatch would look like on a battery and came up with a cost for that particular type of usage, and I just took that cost. Whereas, you could come up with a different usage profile, and if you had some sort of battery simulated testers, you could look at a certain cell and see how they perform under that, and then come up with the cost for that type of usage. Because it's hard, or just a lot of stuff, yeah.
Right. Well, if there's no other question, I would suppose that if you want to talk to the speaker, you still have about 15 minutes here. But otherwise, let's thank him for giving the seminar today.